Hi, in this video, I will be showing you how to find the correlation coefficient of a given set of x and y values, and also to determine whether there is a linear relationship between x and y. So let's take an example where we have a set of x and y values. So correlation is basically on a graph. If you plot these xy points, and you have to determine how the points are related to each other. So let's start by an example here. Say this is my data set. For example, this is the x values and these are the y values you have. So this is a small data set. It only has about 5 values of x and 5 values of y. Now we could easily plot this in a xy graph and see where the points are, but we could also calculate the correlation coefficient and also determine whether there's a linear relationship between x and y. So correlation coefficient is actually very easy in Excel. You just use the function called correl, and you provide the array 1 and array 2. Array 1 is all the data points in x, so everything together, and then array y is everything in y. Array 2 is everything in Y. So you can select that, and just by holding the left button and just dragging, you select the entire array. So you're basically passing two parameters. And if you just see that, you will see that the correlation coefficient in this case is negative 0.163, close to that. Now, the next step we can actually do is determine whether there is a relationship between X and Y values, right? So for that, what we need is, as you can see, the formula is the R is equal to the summation of x of I minus x divided by the standard deviation. So where x bar over here is the mean sample of the variable, and sx is the sample standard deviation. Y bar is the sample mean of the response variable, and sy is the sample standard deviation of the response variable. So basically the mean and the standard deviation, we need to find that out first. So let's go ahead and start by computing the first compute x bar, and then y bar, and x the standard deviation of x and standard deviation of y. So that's pretty easy. You could just compute the, basically we want to compute four things first, right? The mean and standard deviation of x and the mean and standard deviation of y. The mean of standard deviation, you can compute it in several ways. One of the ways is that you would just sum these things up, right? So what is x bar, right? I'm just gonna write x bar here, but it's really the x with the bar symbol on top of it, right? A dash on top of it. So x bar is actually equal to the sum of all the x values. Sorry, this didn't come out good. The sum of all the x values, right? Divided by the number of x values. How many x values do we have? We have 5. So really it did multiplication. I meant to do divide. So x bar is 7. Now you need to find x standard deviation, the sx, but which is also the standard deviation of x, right? So that there is multiple ways you can actually manually do. Like even this mean, I did it by doing the sum divided by thing. You could actually just type the mean and pass just these values, and it should give you the same same numbers. Why is it not giving me the same numbers? Actually, you could just do average. Anyways, we got the x bar. Let's do the s, the standard deviation. Standard deviation also has a formula, or you could just use the Excel function. But if you want to do it the formula way, it would be using the formula. But let's do standard deviation. The numbers, I don't know if I can just pass it like this. So that is the standard deviation. That's a very simple way to do using the Excel formula, or else you have to do like x minus x bar, and there is a huge formula for standard deviation. Let's compute y bar really quick. Now y bar would be nothing but, I told you, the sum of these y values divided by the number of them. So that's 5. Now we need the y, the s of y, so that's the standard deviation of y. For that, again, we'll just use the formula. This, you just pass in all the data set. So that's about 2.91, right? So that's that. What else do we need? The next step is basically just finding these values, so you have x and y. You need to find x minus x bar divided by the standard deviation. So for that, I would just punch in the number here, which is x minus, you can use the brackets. X is 5. What was your x bar? X bar, remember, is 7 for each of the x's, right? That's the mean. So we're just gonna click on this, x minus x bar divided by the standard deviation of x. So that's that value. I'm just gonna put the $sign in front of this in Excel, which means like when I drag the formula the next time to the next row, I don't want it to increment these values. Okay, so that's that. And I could easily just drag this, and you can see that I got that. Then I need the y bar minus. So each of the y's, for each of the y's, let's calculate the thing. Y bar, so take the specific y, subtract the y bar from it, and divide that by the standard deviation. So that is that. Now again, I'm just going to put the $sign because I'm going to drag these formulas and I don't want it to increment when I drag. So that's that. I'll just drag it. So it's done. Now the product, you need to find the product here. What does this mean? The product, basically we are doing this r is equals to what, right? So the pieces of r, as you can see in the formula here, r is equal to the summation of xi minus x. So we are doing each of these components. So this column is basically the very first thing in the summation on the numerator. That's the xi minus x bar divided by sx. This is the second part. Now we need to take a product of both of these. So we'll just multiply the answer of this with this, and that's it. And then you can just drag this. So that's the product. Now it's very easy. You just have to sum this up. You're going to sum these values. So this is giving you the entire numerator. At this point, what you have here in cell 21, K21, is the sum. Okay, so this sum, the next step is you just take the sum and divide that by n minus 1. So let's do it over here. This is the sum divided by n minus 1. N is 5, so 5 minus 1 is 4. So that would give us that value of negative 163. So that is your thing. The linear correlation coefficient, remember, it's always between -1 and 1, inclusive. So if it's positive, like +1, then you have a perfect positive linear relationship existing between the two variables. If it's -1, then you have a perfect negative, and if it's closer to when r is closer to +1, that's a strong evidence of a positive association between the thing. And when r is closer to -1, that's a stronger evidence of negative association. If r is close to 0, then there is little or no evidence existing of the linear relationship between the two variables. So in this case, we will just test whether the correlation between the x and y variables is strong enough to conclude that there is a linear relationship. We need to determine the absolute value of the correlation coefficient. If the absolute value of the correlation coefficient is greater than the critical value for the correlation coefficient for the given sample size, then the linear relationship exists. That's how you conclude it, right? So basically what all you need is that to test whether there's a linear correlation, linear relationship, you need to just test whether the correlation between the x and y variables is strong enough, and I'll determine the absolute value of the correlation. So let's try that. Otherwise there is no. So for the critical value, we have to first find the critical value. You can use the critical value for correlation coefficient table. You can just Google that, or you should have that in your stats book. And if you just look for n equal to 5, the critical value is 0.875. So you see that that is 0.875. Now determine the absolute value of the correlation coefficient. So recall, ours is negative 0.163. So absolute value is basically like positive value of it. So that is 0.163. Now is 0.163 is not greater than 0.878, right? Remember, so all I'm saying is I looked up the critical value and so what I did was I looked up the critical value using the table, right? And for that I got 0.878. okay, now we're just comparing these two numbers, this with this, the absolute value of this, which is basically not negative but the positive thing, right? So you just compare these two, and then if it is since the R value we got is not greater than the critical value, there is not enough evidence to conclude that there is a linear relationship. So that's pretty much it. Now let's quickly show you an example where we would flip this, right? Flip the scenario. Not the scenario. Let's change the numbers a little bit, right? So let's just change the values for. So let's say, so this was our x and y values. I'm going to replace them with something slightly different. So since I'm using a formula sheet, everything got updated automatically. I didn't have to redo anything. But as you saw, the numbers changed, right? This is for a different data set. Now I have these two numbers, right? This was, remember, just this R variable, right? R is equal to the summation of this formula divided by n minus 1. We already did that. So we have negative 68 and 878 still, because our n value is still the same. So even now, what we can do is because the correlation coefficient is negative, right? The correlation coefficient is actually negative. The absolute value is 0.685, right? The absolute value is 0.685, right? And this value is less than the critical value, right? So it's not greater than the critical value. For the data set with 5, there is no, what we can conclude is that there is no linear relationship between this response variable and the explanatory variable. So that would be the answer to this question. So let's review this question one more time. We found the R variable